uh, this is our unit 2, Riemann integral, Riemann. This is your Riemann integral, core to theory of real functions. So we already studied in our last class what is partition. So what do we mean by partition? A partition P of close AB is a set of points that is your P is equal to x naught, which is your first point A, then your x1 x2 like this. Your last point is xn, which is equal to the endpoint B. A partition P of closed AB is a set of points P containing elements x0 x1 x2 up to xn such that your x0, which is equal to A, this thing is less than x1, less than equal to x2, less than equal to xn, which is equal to B. So we already studied this thing. This is a partition. That means if this is your A and this is your B, then this is your x0, this is your xn, then this is your x1 x2 x3 dot like this is xn minus 1, and this is your xn. So this is a partition. And what is your del xi? Your del xi is the length of ith subinterval. Like your first subinterval, this is your x1 minus x0, then second subinterval is your x2 minus x1. Similarly, your del xi means this is your ith subinterval length, that is your xi minus 1. This is your ith subinterval length. So we already studied these things. Similarly, since our f is bounded, here what we will study in this whole unit, our f is bounded. The function what we are considering here, f is bounded. So since f is bounded and I am considering in the closed interval AB, so f is bounded in this closed interval AB. So since in the whole interval it is bounded, so it is bounded in each of its subinterval. That means it is bounded in each of its subinterval. Okay, each of its subinterval means this is the ith subinterval or like. So it is bounded in each of its subinterval. So since it is bounded, so we can take the minimum element or maximum element or the infimum of f and supremum of f. So let small mi, this is the infimum of f in xi minus 1 to xi closed interval. Similarly, your capital Mi, this is your supremum of f where x belongs to, or this is supremum of f of x where x belongs to this ith interval. This x belongs to xi minus 1 to xi. So this is your capital Mi. This is your small mi, which is the infimum of f of x in ith subinterval. Similarly, this is capital Mi, which is the supremum of f of x in the ith subinterval. So if we will find a sum like this is m1 del x1 capital M1, then capital M2 del x2. Similarly, capital Mn del xn, this is a summation, this is capital Mi del xi, I from 1 to n, and this sum is called your upper Darbach sum for a partition P, because here the partition P is the x0, x1, x2 up to xn. And here similarly, if you will take small mi, so small mi del xi plus small m1 del x1 plus small m2 del x2 plus dot small mn del xn. This is another sum. If you write in the summation formula, this is small mi del xi, I varies from 1 to n, and this sum is called your lower Darboux sum for this partition P. So these things we already know it. So if small m and capital M are the infimum and supremum of close supremum of f in interval close AB, then we can say in between small m and capital M, since it is infimum and supremum in the whole interval, so if I will consider in the ith interval, if small mi is the infimum, then obviously small mi is greater than equal to small m, or small m is less than equal to small mi, because small m is the infimum in the whole interval and small mi is the infimum in the ith subinterval. So and small mi is also less than equal to capital Mi, because capital Mi is the supremum, small mi is the infimum in the ith subinterval, and similarly this capital Mi is also less than capital M, because capital M is the supremum in the whole interval. So small mi is always less than that. So if I will multiply del xi small m into del xi, which will be less than small mi into del xi, which is less than capital Mi into del xi, which is less than capital M into del xi, where I varies from 1 to n. So similarly, I am taking I varies from 1 to n. That means taking a summation of n terms. So what we will get? Yeah, the first one is your the m can go to out of this summation I from 1 to n. Then this is simply del xi, and this is your LPF, and this is your UPF, and this is similarly capital M go to outside of the summation. This is I from 1 to n del xi. This summation is your b minus a. We already calculated your del xi, summation of del xi I from 1 to n. This is your b minus a, that means your xn minus x naught. So this is your b minus a. So we can put that m whole into b minus a. This thing is less than so this thing is less than equal to LPF less than equal to UPF less than equal to capital M whole into b minus a. So this relation we know that this thing is satisfying. So this is your relation 1. And similarly, we also know what is our lower Darboux integral and upper Darboux integral. So what is our lower Darboux integral? We know this is our lower Darboux integral of f dx. This is the supremum of LPF, and similarly your upper Darboux integral of f dx. This is the infimum of UPF. And also we know another thing, generally we are calculating supremum and infimum of a variable. Suppose this is your LPF. Suppose LPF varies from this thing to this thing. It means for different partition LPF will vary. Suppose LPF lies between this one, and I am saying lower Darboux integral, this is the supremum of this thing. That means this is the supremum here. This is the lower Darboux integral of f dx, f of x dx. So what we can say, there exists a partition from this thing. This is the supremum of LPF is a lower Darboux integral of f dx. Since this thing holds, so we can say there exists a partition. That is from the definition of supremum. We already know the definition of supremum. There was a second condition. So which told you there exists a partition P of close AB such that since supremum means this is a least upper bound of LPF. So this is the least upper bound of LPF, and since this is your lower Darboux integral, so since this is the supremum, so if you will go a little bit behind, then there exists a P, or there exists a partition P1 of closed AB such that L P1F is greater than lower Darboux integral of f dx minus epsilon. Since this is the supremum, so or this is the least upper bound, so if we will go anything less than that, that is not a least upper bound, because since this is least upper bound, so if you will go anything less than that, there exists a partition P1 for which the LPF is lies in between them. Suppose there is the epsilon, means this length is epsilon. If this length is epsilon and you are coming epsilon less than this value, that means you are coming this is your lower Darboux integral. If somebody will tell no, lower Darboux integral, the LUB lies here, so means epsilon less than that. So if we will go to epsilon left hand epsilon unit towards left hand side, then there will be an LPF, or there will be a lower Darboux sum for a partition P lies in between them. That's why we cannot say this is our lower Darboux, this is our supremum. That's why this is the only supremum. That means there, if we will go epsilon distance behind, then there exists a partition P1 such that LP1F is greater than this one. Similarly, for this one, this upper Darboux integral, what we can say, suppose your upper Darboux integral is lies in this thing, and its infimum means this thing. Infimum means this is your greatest lower bound. If somebody will say no, if I will go to epsilon right hand side, that will be the greatest lower bound. That means if you will go epsilon right hand side, and he will say if I will add this thing f dx plus epsilon, this will be a greatest lower bound. This thing does not happen because infimum of this thing is this one. So if you will go epsilon unit towards right, then this thing is greater than this thing is less than UPF. That means there exists a partition P2 such that in between them, in between them there are some for some partition P2, the UP2 lies in between them, in between this line and this epsilon distance, in between this thing UPF lies. So these things we already told you. Then we did some problems also. So before that we also know how to calculate this lower Darboux integral and upper Darboux integral. So after knowing this thing, if your lower Darboux integral is equal to your upper Darboux integral, suppose this is your lower Darboux integral of f dx, if this thing is equals to your upper Darboux integral of fx, then we will told that this is the integration of f from a to b, and if this thing holds, then we can say that f is a Riemann integrable on closed AB. So if this thing holds, then we can say f is Riemann integrable on closed AB. So these things we already completed. Then also some problems we already completed. Now comes to what is the refinement of a partition. So what is the refinement of a partition? Refinement of a partition. So before going to this refinement, we already know what is a partition. P, this is your x naught, which is equal to a, then x1 x2 like this, xn minus 1, which is xn minus 1, and your xn is your b. This is these things. This is your x naught, this is your xn, this is a b, and this is your x1 x2 dot dot xn minus 1 xn. So this is a partition. So before going to this refinement, I will tell you what is the definition of norm of a partition, norm or mesh of a partition. So norm or mesh of a partition, norm or mesh of a partition is the largest subinterval length, is the largest subinterval length of closed interval AB. So in closed interval AB, how many subintervals are there? So if you will take each subinterval's length, then among them which one is the largest, that is the norm of that partition, and is denoted by norm P. That is the norm. Norm is denoted by this mu. So norm of partition P means that is your norm P, mu P. That means that is your norm P. So that means suppose if you will calculate your first subinterval length is del x1, which is x1 minus x0. Similarly, del x2 is your del x1. This is your del x2. Del x1, then del x2 is your, this is x2 minus x1. Similarly, your del x3 is your x3 minus x2. Similarly, your del xn is xn minus 1, sorry, xn minus xn minus 1. This is your xn minus xn minus 1. This is your del x1, del x2, del xn. So what will be your mu P? This is norm P is, norm of a partition P is denoted by norm P, and is defined as, this is defined in this way. So I can write norm P. This is the largest subinterval length, that it means that is the maximum of del xi I varies from 1 to n. 1 to n. That means this is the maximum among del x1, del x2 dot dot del xn. So what are the ith intervals? That means among all the intervals, this is the maximum or the largest subinterval length. This is your mu P or norm of a partition P. Then now comes to what is the refinement of a partition. So what is the refinement? Refinement of a partition. A partition P star of P is said to be a refinement. A partition P star of a partition P. Here P is also a partition. a partition P star of P is said to be a refinement if P star is a superset of P. So if P star is a superset, if P star is a superset of P, then P star is a partition. So now comes to an example. What we told before. Suppose this is a partition. This is a partition P. Then what will be your P star? That is a superset. That means you have to keep all these points, along with you have to write some extra points. Like suppose x0 is here, I will write y1, then x1 is here, I will write y2, then x3 is here, then I will write y3, then similarly xn minus 1, then yn minus 1, yn minus 1, or I can write yn, then it's not y1, then I can write here xn. So whatever I wrote, just I added some new points like your y1, y2, y3, yn. These things I have added. That's why this is just a superset of P. So that means here I have added some extra points in between a0 and x1. I have added y1. Similarly here y2 in between y1 and in between x1 and x3. This is your x2. So whatever it may be, I just added y1, y2 and some points yn. So whatever the new points we are added, that makes it finer. That means here there was a much more distance. So if I will add some new points here, then the distance decreases. So we can also say that this refinement of a partition P star S, this is a partition which is finer than P. Okay, this is a partition. Also we can say that P star is finer than P, because in P there are points are in much more distance. So if I will add some more points in between them, then it makes P much more finer. That means P star is finer than P, or we can say P star refines P, or we can say P star refines partition P. So if this is your refined Rasmita Amita. Then comes to a theorem. A theorem which is related to this partition. So the statement is, if P star is a refinement of a partition P, if P star is the refinement, if P star is the refinement of a partition P, then for a bounded function f, we have to show that L P star f, this thing is greater than LPF, and U of P star f, this thing is less than your UPF. That means if P star is the refinement of P, then L P star, this is greater than LPF, and U P star, this is less than equal to UPF. So how I will show it? Now prove. Since P star is the refinement, so it has more element. Suppose I will consider P star contains just 1 point more than P. Okay, so since P star is the refinement, of P, refinement of P. So P star has more points than P. Now I will consider only suppose P star contains only 1 point more than P. Similarly, if it will contain 2 or 3 point more than that, then we can easily show. That means it will be okay. So consider P star contains just 1 points more than P. Just 1 point or contains one element more than P or 1 point more than P. Okay, so if P star contains 1 point more than P, let that point be J, and this J belongs to, suppose in the ith subinterval, this J line. That means suppose this is your A, this is your B, and this is your x0, x1, sorry, xn. So these are x1, x2, like this is your xn minus 1, and here are the point xi minus 1, xi. So in between them J is there. So J lies in the ith subinterval. So if J lies in the ith subinterval, let J belongs to this one. That means your xi minus 1 is less than J, less than xi. Since J lies between these two things, so xi minus 1 is less than J is less than xi, and since here it is saying that the function is bounded. Everywhere the function is bounded here. Since f is bounded on closed AB, since f is bounded on closed AB, so f is bounded in each of its subinterval, on each of its subinterval. So these are the this is also a subinterval xi minus 1 to J, then J to xi. These are also subintervals. So also we can say that this is bounded on this subinterval, because here I am saying this is bounded on each of its subintervals. So let it is bounded means it has supremum and infimum element in each of its subinterval. So now I will consider only first I will prove this one. Also we can write similarly we can prove this one, but now I am going to prove this lower Darboux L of P star f is greater than equal to LPF. Let W1 small w1 small w1 small w2 and small mi be the infimum of f on the subintervals on the subintervals the subintervals are xi minus 1 to J, that is your xi minus 1, this is your J, and this is your xi. So this is the whole subinterval xi minus 1 to xi, and since I chosen a point J here, so the new subintervals are xi minus 1 to J, and this is J to xi, and this one. So here W1 is the W1, W2 and Mi are the infimum of f on the subinterval xi minus 1 comma J to xi and xi minus 1 to xi respectively. That means in this subinterval the minimal element is w1 are the infimum element. Similarly here the minimum element is w2, and in whole xi minus 1 to xi the minimum element is small m, small mi. This thing we known before. In small mi is the minimum infimum of f in the ith subinterval. So then what we will write? So clearly we can say your w1, this thing is mi is less than w1, because this is in the whole interval. This is minimum, means in each of its subinterval, in each of this small subintervals, this thing are maximum more than that value. That means w1 is greater than mi and w2 is also greater than mi, because mi is least in, or this is the smallest value in the whole interval, this xi minus 1 to xi. So I can write w1, we can write your mi, this thing is less than w1 and mi is less than equal to w2, since mi is the infimum in the whole interval. Okay, so this thing can be written. Now if I will consider lp star f minus lpf, so what we will get? So this is the ith interval and the rest subintervals are same. That means for lp star f we can write m1 del x1, m2 del x2, that uh, when the ith interval came, so there is one more point in this p star. So for that one we can write this is w1 whole into, because there are two intervals here. So w1 whole into, this is xi minus xi minus 1, this subinterval length, plus w2 whole into this subinterval length, which is xi minus xi, plus dot like your small mn del xn, since n subintervals are there, xn. And what is your lpf? For lpf there is also m1 del x1, and since it is minus is there, so this is small m2 minus del x2. Like this, in the ith subinterval I will write this is small mi whole into xi minus xi minus 1, and then the last one is here, this is mn del xn. So all things will cancel out, so only things left in the ith subinterval, this thing is the only difference. So this is your w1 whole into xi minus xi minus 1 plus w2 whole into xi minus xi, then this is minus mi whole into, and xi minus xi minus 1, this thing can be written as xi minus xi plus xi minus xi minus 1. Okay, minus xi plus xi, then it cancel out. So this thing we can simplify. This is your w1 whole into xi minus xi minus 1, and if you will write this one, then turn में घुमाता हूँ. Then w1 whole into xi minus xi minus 1. Similarly, if you will write for this one, this is your mi whole into xi minus xi minus 1. This is the second one, and this is your xi minus xi minus 1. Similarly, if I will write this one, then this is your w2 whole into xi minus xi, then I will write this one, this is minus mi whole into xi minus chi. So from these first two terms, if I will take common chi minus xi minus 1, this will be your w1 minus mi. Similarly here I can take common, this is x2 minus chi, this will be your w2 minus mi. And since mi is less than equal to w1, mi, this thing is less than w1, so this term is positive. Similarly w2 is also less than, sorry, mi is less than w2, so w2 minus mi, this thing is positive. And here xi is taken in between xi minus 1 to xi, so xi minus xi minus 1, this thing is also positive, this thing is also positive, because xi lies between xi minus 1 to xi, so all terms are positive. So what I will get, this thing is greater than equal to 0, so greater than equal to 0, this implies you can write your L p star f minus LPF, this thing is greater than equal to 0, so you can take this thing right hand side, so your LP star f, this thing is greater than LPF. So this is the first one proved. Similarly we can prove, we can only write similarly we can be proved that UPF, this thing is less than, sorry, okay, UP star F, this thing is less than UPF. Proved. Okay. Then go to a corollary, and it is saying, then the next corollary is if a refinement P star of P contains, if a refinement P star of P contains P points more than P. Here this P are capital P. This thing contains P points more than P. This is small p. Okay, this is small, and all are capital. If a refinement P star of P contains P points more than P points more than partition P, then contains P point more than P, and f of x is, and f of x is, its mod is less than equal to k, that means your f of x is bounded by k for all x belongs to close AB, for all x belongs to, sorry, for all x belongs to close AB, for all x belongs to close AB, then we have to show, that, so first we have to show LPF is less than equal to LP star F, which is less than equal to LPF plus 2pk mu, and similarly, that means we know that in the last theorem LP star, this thing is greater than LPF, and there is also an upper bound for LP star F. Similarly for UP star F, LP star F is lies between this one and this one. Similarly UP star is lying between upper bounded by UPF, and its lower bound is this is UPF minus 2pk mu. So these things we have to prove. So now first go to the first one. I will do only for this one. We can add, similarly we can prove for the second one. So already in the above theorem we proved that. So we already proved that if P star P star has 1 point more than P, has 1 point more than P, then your L P star F minus L P F, this thing is your see this one is your these things J minus xi minus 1 w1 minus mi x2 minus j whole into this w2 minus mi. So this is your L P star F minus LPF. So I will write that point first. So L P star F minus LPF is, this is your j minus xi minus 1, here this one, j minus xi minus 1 whole into w1 minus mi plus w2 minus j whole into w2 minus mi. So LP star F minus LPF is this one, and so now we can write since our f of x is bounded by k for all x belongs to close AB, then we can write this values w1 mi w2 mi. So these things are the infimum values of f. So this thing also lies between minus k to plus k. So we can say we know mi, this thing is less than w1, mi is less than w1, and all these things are lies between minus k to plus k. Since its mod value is lying between k, that means this thing can be written as f of x lies between minus k to plus k. Okay, since this thing holds, so this is one types of f of x, small mi and w1, these are one types of f of x, and mi is less than equal to w1. So this inclusion holds, all these things are lies between minus k to plus k. So if we will take the difference of this middle two, then this is your w1 minus mi, and then difference between the first one and last one, so this thing will be less than k minus k minus minus k, which is your 2k. So this thing is less than 2k, less than equal to 2k. This thing is your less than equal to 2k, and since this is the bigger one, this is the smaller one, we can write this thing is greater than equal to 0. That means 0 is less than equal to w1 minus mi less than equal to 2k. Similarly 0 is also less than equal to w2 minus mi less than equal to 2k. So if I will put these values here in place of w1 minus mi and in place of w2 minus mi, so if I will put this thing, so what we will get, now your LP star F minus LPF is less than equal to, here it is okay, j minus xi minus 1, j minus xi minus 1 in place of w1 minus mi, sorry, this is w1 minus mi, I will put 2k, that's why I will give this less than equal to, that's why I have given here less than equal to, this is your 2k. Similarly this is your x2 minus j, this is your x2 minus j, and this one is your 2k, and less than equal to symbol is here. So if I will take 2k common here, this is your j minus xi minus 1 plus this is xi plus xi minus j, so which is your 2k whole into j can be cancelled out, it will be xi minus xi minus 1. So 2k whole into xi minus 1. So I can generalize this thing. We know our norm P. Norm means this is the norm P or partition P. This is the maximum or the largest subinterval length. That means this is the maximum of del xi for I lies between 1 to n. For I lies between 1 to n. This is the largest subinterval length is your mu p. So if its norm of this partition is mu, that means the maximum subinterval length is mu. Then if I will put this thing, then this will be a 2k mu, because this is the del xi, and the maximum value of del xi, this is your mu, this is your norm p. So if I will put the maximum value, then it will be again less than equal to, so this is your 2 less than equal to 2k mu. So where mu is the norm of p, so norm of p, this is equal to mu say. So what we got here, LP star f minus LPF, this thing is less than equal to 2k mu if this P star contains only 1 point more than P. This thing we got if P star contains only 1 point more than P. So if P star contains small p number of elements more than P, or number of points more than P, then LP star f minus your LPF, this thing will be less than 2 pk mu. If P star contains only 1 point more than P, we are multiplied here only 1, means what is written here, only for 1 point. So if P star contains small p more number of points, then small p can be multiplied on the right hand side. So now this is proved. And similarly, this one, LP star f is less than equal to LPF plus 2 pk mu. And in the last inequality, in the last theorem, we already calculated this thing, LPF is less than equal to this thing. So togetherly we can combine, we can write in the last theorem, we already proved that L P star f, this thing is greater than equal to LPF, or your LPF, or we can say your LPF is less than LP star f. Now if we will combine these two things, so your LPF is less than equal to LP star f is less than equal to, here LP star f is this one. So you will put this thing to right hand side. So this will be your LPF plus 2 pk mu. That means from this one, your LP star f is less than equal to LPF plus 2 pk mu. Okay, so this is now proved. Similarly, we can prove the another. Similarly, other one can be proved. For UPF or for UP star f, so there is also another extension of this theorem. So also extend it. So what is the extension? If P star is the refinement of P, then we know that, I can see for 5 minutes. If P star is the refinement of P, this is the proof. This is the proof of the above corollary. Then also we can extend it for some more results. So what is this one? If P star is the refinement of P, if P star is the refinement of P, if P star is the refinement of P, then we know that, then we know that L P star f or L PF, this thing is less than LP star F, and if P star is any partition, then LP star F is always less than UP star F. That means for any partition P star, a lower Darboux sum is always less than its upper Darboux sum. Also we can say that for partition P star, LPF is less than LP star F, and UP star F is this one is okay for if P star is a refinement of P, then LPF is less than equal to this one, and if P star is any partition, then LP star is less than equal to UP star, and if P star is a refinement of P, similarly we can write for UPF, then UP star F, this thing is less than your UPF. So if we will combine all these things, what we will get? This is the first one, this is the second one, this is the third one. So if we will together combine all these things, we will get your LPF, this thing is less than LP star F, and this thing is less than your UP star F, and this thing is less than UPF. So this is 1 2 3 4, you know, if we will subtract this thing, like your 3 minus 2, this thing is always less than 4 minus 1. So we will subtract this thing. This implies your UP star F minus LP star F, this thing is less than UPF minus LPF. So this is a result. That means if P star is a partition of P, then so that UP star F minus LP star F, this thing is less than UPF minus LPF. This is just another result. So okay, today only this much.